This question comes from Vittorio, who asks, what if a glass of water was, all of a sudden, literally half empty? The pessimist is probably more right about how it would turn out than the optimist. When people say glass half empty, they usually mean a glass containing equal parts water and air. Traditionally, the optimist sees the glass as half full, while the pessimist sees it as half empty. Linguist Gretchen McCulloch points out that we choose which reference state to mention as a way to efficiently indicate whether the glass is currently being filled or emptied. Language is cool. But what if the empty half of the glass were actually empty? A vacuum. The vacuum would definitely not last long, but exactly what happens depends on a key question that nobody usually bothers to ask. Which half is empty? For our scenario, we'll imagine 3 different half-empty glasses: the traditional air-water glass, a vacuum on top glass, and a vacuum on bottom glass. We'll imagine the vacuums appear at time t = 0. For the first handful of microseconds, nothing happens. On this timescale, even the air molecules are nearly stationary. For the most part, air molecules jiggle around at speeds of a few hundred meters per second, but at any given time, some of them happen to be moving faster than others. The fastest few are moving at over 1,000 meters per second. These are the first few to drift into the vacuum in the glass on the left. The vacuum on the right is surrounded by barriers, so the air molecules can't easily get in. The water, being a liquid, doesn't expand to fill the vacuum in the same way that air does. However, in a vacuum, it does start to boil, slowly shedding water vapor into the empty space. The water on the surface of the left glass also starts to boil, but the incoming air will stop it before it really gets going. After a few hundred microseconds, the air rushing into the glass on the left fills the vacuum completely and rams into the surface of the water, sending a pressure wave through the liquid. The sides of the glass bulge slightly, but they contain the pressure and don't break. A shock wave reverberates through the water and back into the air, joining the turbulence already there. The shock wave from the vacuum collapse takes around a millisecond to spread out through the other 2 glasses, which both flex slightly as the wave passes through them. In a few more milliseconds, the shock wave reaches the human's ears as a loud bang. Around this time, the glass on the right starts to visibly lift into the air. The air pressure around the glass is trying to squeeze the glass and water together. This effect is easy to imagine with a wine glass. Air pressure at sea level is around 15 pounds per square inch, so in a typical glass, the water's surface and the glass below it are being pushed down with a force of almost exactly 100 pounds. Normally, this force is opposed by the air pushing up on the bottom of the glass. But in the glass on the right, air pressure pushes the glass up from below unopposed with 100 pounds of force, while simultaneously pushing the water down from above. This is the force we think of as suction. The vacuum on the left didn't last long enough for the suction to noticeably lift the glass. But since air can't get into the vacuum on the right, the glass and the water begin to slide toward each other. By now, the boiling water has filled the vacuum with a very small amount of water vapor. However, the glass and the water are moving too fast for the vapor buildup to matter. Less than 10 milliseconds after the clock started, they're flying toward each other at several meters per second. Without a cushion of air between them, just a few wisps of water vapor, the water smacks into the bottom of the glass like a hammer. Water is very nearly incompressible, so the impact isn't spread out over time. It comes as a single sharp shock. The momentary force on the glass is immense, and it breaks. This water hammer effect, which is responsible for the clunk you sometimes hear in old plumbing when you turn off the faucet, can also be seen in the well-known party trick of smacking the top of a glass bottle to blow out the bottom. In our situation, the forces would be more than enough to destroy even the heaviest drinking glasses. Fun fact, when I was trying to calculate this, I bought a bunch of cheap glasses from the dollar store and then tested, applying different amounts of force to the base of them to see how easy they were to blow out. And one of the glasses just didn't break no matter what I did, so I kept it. It sits on my shelf. It doesn't match any of my other glasses, which kind of annoys me. And every time I look at it, I think thanks, science. So this is why I stick to theory. The bottom is carried downward by the water and thunks against the table. The water splashes around it, spraying droplets and glass shards in all directions. Meanwhile, the detached upper portion of the glass continues to rise. After half a second, the observers, hearing a pop, have begun to flinch. Their heads might lift involuntarily to follow the rising movement of the glass. The glass has just enough speed to bang into the ceiling, breaking into fragments, which then return to the table. The lesson? If the optimist says the glass is half full, and the pessimist says the glass is half empty, the physicist shucks.